In this figure, we see charged particles being shot into a region of constant electric field. In this case, the proton is moving in the same direction as the constant electric field. We will let this direction be to the right or the positive x direction. Remember that the presence of this electric field, this means that a positive charge feels a force pushing it to the right, and in this case, the motion of the proton will remain along the x-axis. Also, if the proton feels a push, that means there must be a force present acting on the proton and a resulting acceleration. If we focus on just one charged particle as it is shot into electric field, how does this force affect the particle's motion? Newton's second law of motion gives us the start we need. If we want to analyze the motion of the proton, we can make our notation a bit cleaner by noting that all of our vectors, the electric field, the force, the displacement, and the velocity, are in the same direction. As a result, we can drop the vector signs and use component notation instead. For the charged particle in the electric field, the magnitude of the force is given by the magnitude of the object's charge times the magnitude of the electric field. This will allow us to replace the force symbol F sub x on the left in Newton's second law with the proton's charge times the magnitude of the electric field. In many cases at this level, the mass of the charged particle is so small that the resulting force due to gravity on the particle is very, very small compared to the force on the particle from the electric field. Thus, in our analysis, we will only consider the electric force in Newton's second law. Combining these equations and solving for the resulting acceleration gives us the magnitude of the charge times the magnitude of the electric field equals the mass of the particle times the magnitude of its acceleration. Solving this equation gives us the magnitude of the particle's acceleration in terms of its mass and the magnitude of its charge. With the acceleration now known, if we know the proton's charge, the magnitude of the electric field, and the proton's mass, we can then use the appropriate kinematics equation to find other quantities. For example, we can find the velocity of the proton at some later time if the initial velocity is known and a time is specified. In this case, we would use the kinematics equation that says the final velocity is equal to the initial velocity plus the now known acceleration times time. From this, we see that the magnitude of the acceleration is directly proportional to the magnitude of the electric field. Additionally, if the electric field is constant, so is the acceleration. In the case of a charged particle with an extremely small mass that is shot into a constant electric field perpendicular to the electric field, the resulting motion is very similar to projectile motion. In both cases, the acceleration is constant. However, the deflection of the particle can be either upward or downward, depending on the sign of its charge. In this figure, we see an unknown charge moving into an electric field pointed straight down. Notice that the deflection is upward. This tells us immediately that the charge of the particle is negative. A positive charge would be deflected downward in the direction of the electric field.